So today we wrapped up our first group of isometries by proving that reflection across a line L is indeed an isometry. And to do this proof, we relied upon the definition that a reflection across a line is defined by the reflected image of any point having the property that that segment which connects a point to its image, PP prime, is perpendicularly bisected by L, our line of symmetry, or what we may call the mirror of our reflection. So in our diagram here, we start with a point P, and its reflected point P prime satisfies that L is the perpendicular bisector of PP prime. And so in our analysis figure down here, we start with two arbitrary points P and Q, and we have to show that after we reflect those points across the line L and get P prime Q prime, what we want to show is that the resulting segment P prime Q prime is congruent to the original segment PQ. If we can show that for any 2 points P and Q that this must be true, then we've shown that reflection is indeed an isometry. So what goes into that is first choosing the figure that we have on the right, which places P and Q on the same side of the mirror as one another. Then under that circumstance, PQ, Q prime, P prime ends up being a trapezoid. And it's a trapezoid because PP prime, the segment on this side, and QQ prime are parallel one to another, first of all. And that also, as we will see, there are also congruent angles and segments in this figure sufficient for this to be a trapezoid. But we can't say that right off the bat because that actually assumes what we're trying to prove. So the way that we do this is we start by taking the quadrilateral PQ, Q prime, P prime, and subdividing it by taking the point at which PP prime crosses the mirror, calling that point R, and then divvying up our trapezoid into triangles in that way. And then we can use the side-angle-side congruency criterion to show that this triangle, QSR, is congruent to this triangle, Q prime SR. Those two are congruent because of side-angle-side and the definition that Q prime is the reflected image of Q. And so because those two triangles are congruent, all we really need out of that congruence is the congruence of the segments QR and Q prime R. And so now we have those segments being congruent. Also, the other thing we get out of that is the congruence of the angles. Here, QR prime, or QRS and Q prime RS are congruent with one another. But if they're congruent, then so too are their complementary angles, PRQ and P prime RQ. And now that those are congruent, we have yet another side-angle-side congruence argument that we can make, because PR is congruent to P prime R by definition of reflected image. And therefore, side-angle-side congruence can be invoked one more time, but this time on these triangles. PRQ and P prime RQ are congruent triangles. But now that we know that those triangles are congruent, all we really needed out of that was the congruence of the corresponding sides, P prime, Q prime, and PQ, which is exactly what we were trying to prove. So that proves that as long as we pick our 2 points P and Q from the same side of the mirror, that the transformation which reflects those points across the mirror preserves distance. But since that's not the only analysis figure that we could have, we need to also show that the conclusion remains true if P and Q started on opposite sides of the mirror. And that's what the diagram on the left side of the screen does for us. So here we've picked P and Q from different sides of the mirror and reflected them across. And again, what we need to show is that PQ, this distance, is congruent to P prime Q, this distance. But now those two line segments intersect one another, and so things are a little bit more complicated. We introduce the point U, which is their point of intersection, and that cuts the two segments into lengths. Let's call them X and X prime and Y prime. And what we'd like to show is that X plus Y is the same as X prime plus Y prime. But we do that, again, by using side-angle-side to establish two sets of congruent triangles. The set up here on the top and the set down here on the bottom are both pairs of congruent triangles. And from those congruences, what we really need from them most is to be able to argue for the congruence of these two segments, so QU and Q prime U, and then also the congruence of the segments P prime U and PU. But since all of those are congruent, that means that when I add this segment and this segment together to get PQ, I get the same result as when I add this segment and that segment together to get P prime Q prime. And that proves that even if my points were chosen on opposite sides of the mirror, their distance is still preserved when we reflect those points across that line. Finally, we concluded by looking at how to characterize translations, rotations, and reflections based on the characteristics that they share or they don't share. We know that each of them, because we've proven it, each of them is an isometry, and therefore it preserves the distance between any 2 points, PQ and P prime Q prime must be congruent. But among translations, rotations, and reflections, only 2 of them also preserve orientation, or what's called directed distance. Translations and rotations do. And so those get called the direct isometries. Reflections do not. They don't preserve orientation. They don't preserve the directed sense of an angle or the directed sense of a segment. And so it sets reflections apart from translations and rotations. Thirdly, we also talked about the property of moving every point the same distance. In other words, that for 2 points P and Q, is it true that PP prime is equal to QQ prime? Is the image as far away from the pre-image for one point as it is for another? And for a translation, the answer is always yes. But rotations and reflections both move different points, different distances in general. And so that's another thing we can use to distinguish between these 3 types of isometry. But we want to take that a step further in preparation to really see how to characterize all isometries as one of these or the other, hopefully. We decided to look at the notion of a fixed set, which is an answer to the question, what points stay put under one of these transformations? For a translation which shifts every point a uniform amount, as long as the translation is non-trivial, the fixed set of a translation is empty. Every point moves at least a little bit, so it can't be the same place that it was after a translation happens. Compare that with a rotation. Under a rotation, every point does move as long as my angle is not commensurate with 2 pi and is not equal to 0. But there's only one point which doesn't move under a rotation, and that's the center of rotation itself. It stays put. So if I have an isometry whose fixed set is only a single point, maybe we'll be able to say that that isometry must be a rotation. Likewise, for a reflection, when I reflect across a given line, a given mirror line L, every point that's already on that line stays exactly where it was. So in a reflection, the fixed set is every one of the points along that line over which we're reflecting. So we might be able to say later on that if I have an isometry that fixes an entire line, then maybe that means that my isometry must be a reflection across that line. These are the kinds of assertions we'd like to be able to put on a firmer ground in Chapter 8, where we're going to start using the fixed sets of isometries to characterize their type.